get somebody else in here. There we go. All right. I think. All right, moving on. Chapter 4. Without going into big long spiel, this is where I say this is where the power of algebra really starts. We've solved equations. And now we're looking at relationships or equations that describe relationships between different quantities, different values. And we can use those relationships or equations to predict future values or recognize trends, things like that. So we get these equations that are called equations in two variables. There's going to be two different unknowns in them, or one value depends on whatever you put in for that other value. And we'll see today, they're called linear. There's that written line because the relationship actually creates a line. We start by graphing these relationships and recognizing some patterns from the graphs. Our minds are pretty good at recognizing patterns visually. So graphs often give us a head start in understanding data. Different kinds of graphs you've probably run across or worked with. Like pie graphs. Pie charts are pretty good for giving relative percentages. If the whole thing represents 100%, well, maybe that's much as my bills and that much as my food. And then there's all those other little sections or something that you could use the picture to kind of get the feeling of where's the money go, right? Or I do this one every month. I get my electric bill, right? I look at that little bar graph. Bar graphs are pretty good for, comparing moments in time. How much electricity did you use, or what's the spending from year to year, or something like that. Bar graphs. And sometimes you've got data points, right? Like, oh, I've got some results and it kind of comes back like this. Well, you might do this kind of thing and say, is there a pattern or a trend there? I make something a little less choppy there. A lot of our relationships come from actual recorded data, right? Statistics does that kind of work. Well, all right, we've got these values, these data points, and gee, I can kind of see it looks like it's going like that. There's a pattern that I can recognize, a little high and a little low here and there. Okay, well, so there are different kinds of graphs or that describe different patterns. The ones that we're all going to be looking at in this class are all what we call linear patterns. That is, they have a steady rate of change. They go up kind of at the same rate. We're going to call that slope, or maybe they go downhill at the same rate. Think about mileage. If I'm traveling at this speed, it kind of depends how long I've been traveling. If I travel at that same rate of speed, my distance is gonna climb at a steady rate. So there are different kinds of relationships that we graph. And we're talking about situations now where there are equations that we come up with that can actually describe these patterns. If I throw a projectile or launch a projectile, we can graph its altitude in terms of time, and they always kind of create this, what we call, that one's upside down, but a parabolic shape, just because of the physical forces working on it. And there's equations that can describe exactly that altitude at this point in time, right? More complicated than what we have to deal with in this course. Or, the one we talked about over the last year, flattening the curve, right? Exponential growth, like I used to say, it's like multiply by rabbits. Like rabbits, you start with 2, and then they produce 4, and then they produce 8 and 16. So you start somewhere, then all of a sudden it grows. Over time it starts growing very rapidly. And this is that idea of flattening a curve that we were trying to work on over the past year, you know, but don't let it grow too fast. You know, let's hopefully we can get to a vaccine before it goes crazy. Yeah. Some relation, again, equations, an equation that can describe that particular relationship. Some are very cyclical, like anything having to do with rotation. You know, tides going around the sun, you're going to get those wavy shaped graphs, right? So, and again, equations that can describe that. If you think of that might look recognizable as something that you might call a sine wave. Sine being one of those trigonometry functions, if you've ever heard of that, that could be used to describe that. Anyway, graphs. We're going to deal with lines for our graphs. So we got to start kind of the basics as always. What is this thing on the board? Right? I tried to warn you, you want to have some graph paper today for our exercises. First of all, we've looked at a number line before when we were just trying to find relative positions of values, you know, greater, less than, and we just needed that one number line. And we could say a certain value, you know, lives on the number line right there, or maybe it lives on the number line right there. Well, if I'm dealing with an equation, let's say that was some number x, right? Some number x equals, looks like a -4, huh? Well, if I have an equation that has two variables in it, I need to be able to identify the value for both of those variables. So we use what's called this Cartesian coordinate system, or the XY plane. Right? We take our plane and we use two axes, right? We use two axes to divide that plane, not only in this direction, but in that direction. For most of our abstract or general problems, we tend to use the variables X and Y. We've seen them already quite a bit. So I'm going to label that horizontal axis as my X value axis. And if I've got a Y value to go with it, it's going to go on this vertical axis. We still kind of tend to think left to right, positive, or, you know, smaller to larger in our x-axis. So like I might write in some numbers like this. Those got to skip some just for spacing. Oh, I'll try to write a little bigger. I know my graph is a little smaller. And for the y-axis, up is considered positive, and down is the negative, right? Up and down, positive, negative. If we draw those axes, an axis, that's what we call these, the axes now. The x-axis, right? And the y-axis. Axes with an ES for plural, right? And drawing those on a plane divides it into 4 quadrants, 4 corners, right? And so we just want to understand, if we start talking about specific quadrants, which one are we talking about? How do we label them? We use Roman numerals. We start over here for some reason. That's the one kind of we use a lot. Talk about that eventually. And then we go counterclockwise. This is the second quadrant, the third quadrant, and the fourth quadrant. Just some general ideas here, right? And if I want to then start counting in this system, well, here's my center point, and I have not moved in the x direction at all or in the y direction at all. So this is called 0, 0, 0, or the origin. You say that point there is called the origin. Now, if I think about a position in that plane, like what if I put a point out here somewhere in the middle? It has now both an x dimension, how far in the x direction, left or right, horizontally did I move, and a y dimension, how much up or down did I move. So every point is identified with what's called an ordered pair a pair of numbers and there's an order to them, okay? We wrap them up in parentheses. Here we go, using parentheses for something else again. And the first number in this pair is the x value for this position. And the second number is the y value. So that is very important. That's why it's called ordered pair. You got to do them in the right order, right?
So am I understanding that anything on that bottom left-hand quarter is going to be a negative number, and then anything above that is going to be a positive number?
Yeah.
Okay. Okay, thank you. Sorry, my dog got really excited.
You're about 1 step or 2 steps ahead of me there, okay? Because I wanted to talk about those coordinate values, and then we'll describe, yes, those patterns that you're recognizing already. Good. So this point has 2 coordinates, an x coordinate and a y coordinate that we use to identify its position in the plane. What is the x value for this position? Well, from 0, I went over 1, 2, 3. Hopefully you can see that well enough. So its x value is 3. And its y value, well, y went up from that origin, went up 2. Right, trying to draw there. So the coordinates for that point are the coordinates 3, 2. X is 3, y is 2. Okay. And of course, depending on where I am in the plane, every location is going to have different coordinates. Right, going to have different coordinates. As sorry, whoever that was just sort of suggesting you can recognize some patterns for each quadrant. Notice if I'm over here like this point, the x values are always positive and the y values are always positive. So in the first quadrant, both values are positive. If I happen to be back here someplace, right? Well, my x value has gone negative, but my y value is still positive. Just general patterns here. And if I'm way down here, right, both the x and the y are negative. That's where you fall asleep. And over here in 4, well, the x value I'm positive, but the y value is negative. So kind of general expectation, if I've got a point that's over here, I expect its coordinates to have a positive x value and a negative y value. Okay. And let's see, just making sure I stick with my notes here, right? So, I'm kind of filling up my graph. Can I erase? Is that good enough? All right, there we go. Maybe you want to start a second one for yourself or something like that. You've got your graph paper handy. So we want to be able to identify the coordinates of a point. Now let's see if I make something over here.
Can I ask a quick question?
Okay.
I thought I read somewhere in the syllabus that you would provide our graph paper that we could print out.
It's there in MOM.
Okay, I didn't see it.
Yeah, it's
in this week's folder.
Just below the calendar. There's a purple bar. If you click on it, there's links to several graph paper.
Thank you.
Styles. Okay. Yes. All right. So here's a point in the plane. What are its coordinates? The coordinates allow us to find its location, right? Oh, that reminds me of something else that kind of usually like to say, but I'll say it in a second. So what's the x value? Well, all right, first of all, a convention, I guess. If we don't mark anything else, we'll assume every line represents 1 unit. We got to watch out for that down the road if we start dealing with, say, applications where there's big jumps between units. You got to make sure you understand what the units are for each line. But the convention that we'll live with is, okay, one unit per square, unless otherwise indicated. All right. So here I went 1, 2, 3, 4, 5, -6 in the x direction. And I went 1, 2, 3, 4, I'll call it 5 in between my lines, sorry. So there are the coordinates of that point in the plane. Okay. So we want to just be able to do that for any position in the plane. Count the squares. something like that, right? 1, 2, 3. I went over 3 in the x direction, but I went 1, 2, 3, 4, 5, 6. I'll call it down 6. -6 in the y direction. So there are the coordinates of that point in the plane. If I've got a point that's on one of the axes, that means I didn't travel up or down or sideways, one of the dimensions, one of the directions. So one of those values is always 0. We refer to that as an intercept. It sort of intersects, right? Intercept that axis. This would be a point that is an x-intercept. It's intersecting the x-axis. So its coordinate will always have a y value. I say this over and over to try to help remind you. If I'm on the x-axis, it's always the other one. It's the y value that's 0. The opposite is 0. I didn't go up or down at all. But how many x's? I did 1, 2, 3, 4, 5, and 0. So there's the coordinate of that particular point on the axis. And something over here on a y-axis, I haven't moved left or right. So my x value is 0. But I went up 3. There are its coordinates. All right. Yeah, I mentioned I usually like to say this system is called the Cartesian coordinate system. Cartesian coordinates, cartography, graphs, maps, right? Maps are full of those grids where you figure out your longitude, latitude. René Descartes was a French mathematician in the early 17th century. There's his name in there, right? René Descartes. Just a little background history, right? He invented a system. Oh, let's make a grid and then we can overlay it and we can figure out where you are on the ocean. So, Cartesian right? Cartograph, coordinate system. Okay, little side trip right there for a second. All right, so if we have a point, we want to be able to figure out its coordinates, or if we have coordinates, we want to be able to plot the point. Where is that point in our plane? I'm changing graphs here. My x value is 7, so I count over 7. 1, 2, 3, 4, 5, 6, 7. Means it's over here somewhere. My y value is -2. So down 2, 1, 2. Or from there, down 2. So that's where that point is in the plane. Over 7, down 2. Right? Or if I have -5, -4 as the coordinates of a point. Both values negative. Gee, must be over here, third quadrant someplace. -5x, 1, 2, 3, 4, 5. -4y, 1, 2, 3, 4. Roughly there on my graph. The location of that point in the plane. All right, the beginning step. How to think about using the graphs, all right? There we go. What does that have to do with equations? Well, so then we get our 2 variable equations. We have a couple forms that we're going to see, or a couple shapes for these equations. One we kind of actually saw already when we were dealing with formulas. Here was one, for some reason they made up this formula with these letters and made us move things around. Well, there's a reason we kind of primed you with that. Here's one particular shape. The variables in here are the x and the y, as usual. All right, it's going to be kind of normal. That means the m and the b are numbers, coefficients, right? The m is some number multiplying the x, and the b is some extra number that might be hanging out at the end, plus minus something. All right, so there's one typical shape. The other one that we work with a lot kind of looks like this shape, where most everything's over on one side, and here's our x's and y's again, 2 variables, unknowns, and they always have to add up to something. All right, they add up to something. And so what we kind of want to start imagining is, well, what kind of answers or solutions might we have to an equation that looks like this? For instance here, I'm gonna move on, here we go. If I had one that was in this shape, what if I had one that looked like this? Right, here's an equation that's in that first shape that I mentioned. And this one's kind of saying the y value is a result of all this other stuff over here, and there's another variable. So you can imagine, I could get an infinite number of solutions. If I pick a 1 for my x value, there's a certain number that I end up getting as the corresponding y value. 1 times 2 plus 5. Oh, if x is a 1, then y turns into a 7. If I pick a -3 for my x number, -6 plus 5, the y turns into -1. So I get an infinite possible set of combinations. I can pick any number I want for x, and I'll get some y value that will go with it. So I get an infinite number of possibilities. Even one that looks like this, saying, oh, that always has to add up to 12. I could even use fractions, right? I could put fractions in for this. Well, if x is a 1, then y's got to be 4.5, mental math real quick, or something like that. But if x is 4, then y has to be 0. X goes up, y has to go down, so it always equals 12. But I could come up with an infinite number of possible combinations. Not saying it's anywhere over on the plane, but I can always put some x with some y values. And so what's the result of that? Well, we get this pattern of infinite number of solutions. So for instance, let's just consider this one. I kind of said if I made an x a 1, we're going to do a lot of this in a minute. I build these are called like T-charts. Just a framework. I'm going to put an x number in here and a y number in here. Right? If I put in, say, a 1 for the x, right? 2 times 1 plus 5, I get 7 must be the y that goes with a 1. So that's actually an ordered pair point on my graph. 1 for x, 1, 2, 3, 4, 5, 6, 7 for y, something way up there. What if I had, say, a 0 for x? I'm going to try and come up with like 3 spots here. If I put in a 0 here, 2 times 0 plus 5, oh, I just get 5. There's another ordered pair. If x is a 0, right, I'm on the y-axis, 1, 2, 3, 4, 5. If I kept doing more, I could get more examples, more points. What we want to do is recognize there's a pattern there. Now I picked a 1, I jumped to 0. Here I suggest maybe I jump to -1, -3, jump, 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 and I got these discrete specific points. But if I had chosen some fractions in between, I'd get even more sample points. Possible combinations of x's and y's that go together that would, make this equation true. What you're getting at is, notice, connecting all the dots, you get a line. That's this concept of a linear equation. All the possible x's and y's that go together that make this true, we connected them all end to end, they create a straight line. Okay, don't want to get too far ahead or get too deep into things. Don't get ahead of myself. All right. Just kind of like we did at the beginning of last chapter, or chapter 2, verify. Is a certain ordered pair a solution to an equation? So let's say I've got this one. Here's an equation in that second shape I described where the x's and y's are both on one side, but somehow they have to always add up to 6 for some reason, some situation. We're building, equations and starting with, you might say, simple numbers, working up toward ones like this that are actually describing relationships out there in the real world. Verifying, well, is 3, 0 a solution? Just like our equations in chapter 2, a solution is a value that makes it true. Now, here I need 2 values. Every solution has to have an x and a y, the x and the y that go with it. So if x is a 3, right? First number 3 is an x, second one is a y. If x is a 3, then I get 2 times 3 plus 3 times 0. I'm plugging them in. Does that equal 6? 6 plus 0, yes, equals 6. All right, so that one is a solution. All right, how about, 2, 0? Does that one work? Well, 2 times 2 plus 3 times 0. 4 plus 0. No, that one's not a solution. So the idea of verifying is that you're given a point to test. Plug in the x value in your equation and the y value in your equation and work it out and see if you end up with a true statement. Do those numbers actually equal each other? That's verifying. Okay. I bet the first couple of problems in 4.1 or 2 might ask you to.
Is the x value always going to be the first number in that point?
Absolutely. Yes, that's why I call it ordered pair. It's in order, x and then y. Yes. Yeah, good. Drill that in. Don't get that mixed up. All right, so, well, now we want to kind of work the other way around and come up with our own solutions. Kind of what I was doing a minute ago with that table of values. And come up with one not too tricky. Here's one of those in that other shape, that first shape. You might just generally recognize this is the same shape you actually solved a word problem for in the last chapter, where, all right, you pay $3 for every one of these you buy, and then you get to deduct $1 for some reason. If I spent $10, how many did I buy? Remember, you had a number over here, and then you actually had to solve for the x to figure out how many minutes or how many miles did you actually drive. That was one specific example of that situation that could be described with an equation that, and depending on how many miles you drive, you could come up with a different answer. Well, so we want to come up with some solutions for this equation. So our first technique in this chapter is just pick some numbers to put in and then do the math to simplify and see what you get for the other variable. Pick a number for one of the variables and then see what you get for the other one. When it's in this shape, usually it's easiest to pick an x value, because then you do all the work over here. Whatever you get is the corresponding y value. So nice whole number or integer value there, multiplying my x. So picking some easy, you get to pick any numbers you want. Sometimes the problem will tell you to use this, this, and this. But I like to pick nice, easy numbers, maybe some a little negative, something a little positive, you know. But I'm just going to say I'm going to pick those 3 numbers to plug in. You may know this idea. Any 2 points actually define a line, right? Any 2 points, you can connect the dots and get a line. A third point just kind of confirms we got the right stuff. Right? Okay, so if I put in a -1, if x is a -1, here's where I'm saying I get 3 times the -1 and -1. -3 minus 1, that means the y that goes with it is a -4. There is one ordered pair. That is a solution to this equation. I figured it out by saying if x is this, what does the y have to be? You just put it in there and see what the y comes out to be. What if the x is a 0? 3 times a 0 minus 1. Well, that 0 minus 1 is a -1. So there Notice here, I've got this kind of set up. These are ordered pairs, 0, -1. What if x is a 1? I'm just plugging it in for the x. So here's like 3 different problems in one I'm doing, right? Three different tests. 3 minus 1, a 2. So 1, 2 is another solution to this particular equation. This is still kind of working in, I think, section 4.1, where we're finding solutions to these equations. 4.2, we actually kind of just do more and more of this, and we graph them using this technique. Find some points and then put them on the graph. Like -1, -4, right? -1 for x, 1, 2, 3, -4 for y. There's that one point that happens to be a solution to this equation, graphically. What's this next one? X 0, y -1. 0, x, y is -1 there. How about this one? If x is a 1, y is a 2. And if I do that at all neatly, so my graph paper is nice, right? Those all line up. Line up, exactly. They're on the same line. What that line is telling us is any position, any point, any combinations of the x and the y that are on that line would be a solution. We like the nice numbers, but we could put in a fraction. If I put in 1/2, I'm going to get a fraction for y, but it'll be here on this line someplace, like right about there. Right? When I draw these lines, I usually like to put in the arrows on the end that imply, just kind of like the axes. It goes on forever, right? I could find some y value that goes with any x I pick, or some y value that goes with every x I pick. So that graph line goes on forever. So, table of values, just coming up with solutions yourself by doing the calculation. How about one of those in the other shape here? Yeah. Now these equations, the ones that are in this shape, I'm just going to be honest with you. We're going to give you nice numbers to work with to practice this equation shape. Well, this is kind of like saying, oh, I sold $2 adult or children's tickets and $5 adult tickets. Oh, I'd probably say plus, and it added up to $20. How many did I spend? Or something like that. Always have to add up to 20. But picking nice numbers for x and y so that it kind of works out, not being too messy. If they were just real random numbers, that would be very messy. Notice how the 2 divides into the 20 and the 5 divides into the 20. This is the nice numbers that you're going to run into in our practice problems. You should look for that. Most of the time, I think you'll find that will be the case. Why is that helpful or important? Well, because it makes picking a 0 a good number to test. I'm going to pick a 0 for x and see what comes out as y. If I put in 0 for x, all right? So this part goes away. 0 minus 5y is 20, or just leave off the 0, right? Negative 5y is 20, dividing by negative 5. Y must be negative 4. I'm not showing every detail. I hope I don't lose you there. I hope you're comfortable enough with, if I divide both sides by negative 5, this is where I get. That means when x is a 0, the y is a negative 4. When it's in this shape, consider, I'm going to now go the other way and put a 0 in for the y. So instead of just picking a bunch of x numbers, which I suggested for that other shape, picking 0 for x and then 0 for y, take turns. is often a good way to get nice numbers. If I put in 0 for y, now make sure you put it in the correct position here. 2x minus 5 times 0. So that's going to be 0, right? So 2x is 20. X must be 10. Oh, okay, so there's two ordered pairs. And if I was interested in doing it, I could graph those 2 points. 0, -4, and 4. That's a y-intercept, right? It's on the y-axis, the x is 0. 10, 0, well, hold on, I'll probably run out of hash marks here. 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah, why not here? That's my x-intercept, right? So that particular line looks like that. So picking some numbers to plug in and test for yourself. All right. And let's do that again. -2x plus 3. All right, I'm going to give you some numbers. Can you plug in these 3 values to that equation and find the corresponding y value that goes with it? Right now, I know I've got the first half of my ordered pairs. I need to find the y that would go with it. Time here. Yeah, right. Yeah, watch out for that negative, right? For this shape, we sometimes say the y depends on the x. The y depends on which x value. Or y is a, you may have heard this term, a function. Y is a function of x. It's the result of the x value. I put in the -1. 2 plus 3, is that a 5? If I put in the 0. One more, right? Hopefully you're not too far behind. I hope you're not behind me. Put it that way. If I put in the 1, I don't need the parentheses really, but -2 plus 3 is just 1, huh? There are 3 solutions to that equation. To get there, or if you really got lost or had trouble, see if you can figure out why. If I put those 3 points on a graph, they should all be on the same line. 4.1 doesn't really ask us to do the graphing yet. 4.2, we're going to just continue doing this and then we connect the dots. That's all. So we're kind of trying to see if we can just kind of keep going and get right into 4.2 also. All right, there's that one. Let's do another one. I'll give you one the other shape where I suggested the zeros would work pretty well. And how about that one? Again, I'm just going to tell you, let's just do these 2. Picking a third one, it's kind of tricky if you want to come up with nice numbers. That's why the zeros work so well. Just make sure, it's like, oh, first I'm doing the x, and then I'm doing the y. try to say things that always warn you.
Is there a reason why you, instead of doing it the -101, you started with 0 this time?
Yes. For instance, if I put in a -1, now this one won't turn out too badly because everything is even number, but it's really easy to run into fraction answers, which are harder to plot. Right here, I got -4 plus 2y equals 8. The -1 wouldn't have worked badly for this problem. 2y equals 12, so y equals 6. That would have worked. Let's see if I picked 3. Well, just because they're even, it's really going to work out pretty well either way. I picked an example where both numbers are even, so no matter what I pick, it's kind of always going to be divisible by 2. It worked out nicely. But if this was even, that was odd, 3 and 5, or 2 and 5 or something, you'd end up with fractions pretty quickly.
So how are we supposed to know what numbers you want to work with? Am I getting that it's just going to be numbers that end up being whole numbers and not like incomplete, like improper, like numbers, like fractions? Is that where you're going with this?
We're kind of getting there, but there will be times when you, well, you will almost always use a whole number, but how to choose?
Yes, how do you choose what numbers to use?
How to choose. I'm suggesting if the equation is in this shape, the easiest way to do this is probably by using the zeros. And you're not going to, I'll do one where it's a mess in a second, put it that way, okay? If I put, let me just finish. If I put this in 0 for y, is x a 2? Is that, I did that kind of quickly. Is that right? 2, 0? Did you get that? 2 times 0, 4x must be 8, so x is a 2. But there are the 2 points that I came up with for that line, for that equation. And if I put them on my graph, I could connect those dots. Almost feel like you want me to go faster when you ask the question because you know I'm kind of getting there. If I had, just for instance, this 2x plus 5y equals 10. Now both of those numbers divide into 10, so the zeros again would work nicely. But let's say I just picked a 1, right? If I picked 1 for x, or -1, I'll just make it even +1, not even worry about the negative sign right now. If I put that in here, I get 2 times 1 plus 5y equals 10. So 2 plus 5y is 10. Subtract the 2. I get 5y equals 8. Oh, y has to be 8/5, the fraction. So see how you can, in this shape, you can kind of easily run into fraction in your ordered pairs. That's where I was trying to say, just for practicing with this shape, you're going to find that these numbers, I call them nice numbers, to always tend to divide evenly into that one, just for us to practice with. There's nothing special that says it will always be like that. But it makes using the zeros kind of almost like cheating. Using the zeros will be the easiest way. Did that make sense? That's why I chose the zeros, because other numbers might easily produce fractions, which are harder. You have to sort of guesstimate where on the graph 8/5 is, and so on. Okay. There's no complaints about that. We'll keep going. So, graphing. How am I doing here? Yeah, well, I got a couple minutes. So maybe I'll just end generally today, and we'll pick up more on 4.2 tomorrow and get into 4.3, I suspect. 4.2 is going to present you those kinds of equations, ask you to fill out a table of 3 values. Some problems might give you the 3 numbers to plug in. Some might just say, you get to pick 3 numbers, plot 3 points. Oh, what 3 numbers do I want to pick? Well, here's where I've been saying, you can pick just about any whole number and it will work very nicely in there. And if it's in that other shape, take a look and see if the zeros probably are the easiest way to go. What if I had one that looks like this? A fraction here. And I have to pick numbers to plug in there now. I'd really like to kind of avoid the fraction. Not necessary, but it's kind of nice if I can avoid the fraction. What would be good choices for x's to plug in this situation? Well, any number that's divisible by this denominator, any multiple of 3 would be a good choice, like -3 or 0 or 6. Something that works nicely with the fraction is kind of what I'm getting at. So that's what, we'll do this specifically tomorrow. We'll pick some nice numbers to go with a fraction like this. And then of course there's some weird ones we always have to look at. What kind of line is that? But it looks like I'm about out of time today, but that's good. That's a good start, 4.1. I always kind of say 4.1, 4.2 to see how far we get. We really kind of did half of 4.2. Conceptually, once we have those ordered pairs, all we're going to do is put them on the graph and then connect the dots. That's what 4.2 is going to ask you to do, graph the line. Something in MOM you'll want to get used to when you're graphing. There's a little tool, it's a little pencil tool. Basically, you have to like grab the tool and put at one dot, and then go and put your second dot, and it'll connect the dots with a line for you. You use there's a little pencil tool in there usually. If you run into trouble, bring it up in class, we'll figure it out. Okay, without hemming and hawing and meandering too much right now, I'll stop. But we introduced the coordinate plane and then started finding solutions to these linear equations with 2 variables. And we'll pick it up tomorrow. Okay? I hope so. All right, let's see. Most of you got all that last chapter stuff out of the way and done, but don't forget you got homework due tonight. Okay? All right, folks. And I'll check back in later on, for any messages or questions you might have. But, as always, send me questions. All right, take care. Have a good day, and I'll see you tomorrow.
Okay. Take care.
Thank you. You too.